Hi there, welcome to High School Maths. Today we're going to be looking at similar shapes or similarity, and we're going to start off by looking at an example on similar lengths. So here we've got two pool tables, different sizes, but similar shapes, and what we want to do is find the missing length, so we'll call this, we'll just call it x. And here, what we want to do is, in similar shapes, all the dimensions should be proportionate. So this is 75, this is 50. This one here is 180. This is x, this is the one we want to find the length of the smaller pool table. Now, what we've got to do is find a scale factor. How much bigger is or how much smaller is this one compared to the bigger pool table? Okay, so we want to find how much smaller this is. To do that, we find something called a length scale factor. Okay, so we're going to compare the lengths. Now, we want to find the length of the smaller pool table, so we're looking for what's called a reduction scale factor. That means we put the bigger number on top of the fraction here. So we're comparing the widths of the pool tables because we know the width of both of them, 75 and 50. But we're going to put the smaller one on top because we want a reduction scale factor, so 50 over 75. Now with fractions, where possible, simplify. These are both divisible by 25, so that would become 2/3. Sometimes these will be calculator, sometimes non-calculator, so it's always good to practice that a little bit. And what that's saying is the small pool table is 2/3 the size of the larger pool table. So here, x, which is our missing length, is going to be 2/3 the size, or 2/3 times 180. Okay, and again, you could do that quite easily without a calculator. 180 divided by the bottom, so divided by 3 is 60, times 2 is 120 centimeters, and that's your missing length for the pool table. And the same kind of idea works for enlargement. You would just have the bigger number on top of the fraction at the very beginning line there. So that's how you deal with a length scale factor. Area scale factor works in a very similar way. So you can see here we've got a little picture. This one here is 5 centimeters wide, this one is 8 centimeters wide. The area of this one is 60 centimeters, or 60 square centimeters. We want to find the area of the bigger one. Now for that, because we're looking for a missing area, we need an area scale factor. But we don't know what the area scale factor is. All we can compare just now is the 5 and the 8, the widths of the two posters, because that's the only two dimensions we've got that are the same. So we're going to start off the same as we did last time, with a length scale factor. But this time, we're looking for the area of the bigger picture. So the length scale factor is going to be 8 over 5. That one doesn't simplify this time, but we don't want a length scale factor, we want an area scale factor. And to convert that into an area scale factor, all we have to do is square the fraction. Okay, so we square the length scale factor, we get the area scale factor. To square a fraction, you square the top and square the bottom. So 8 squared is 64, and 5 squared is 25. Okay, so 64 over 25. Again, that doesn't simplify, so we'll probably use a calculator for this one. Our missing area, so the area for the bigger picture, is the area scale factor times the smaller area, 60 cm squared. Okay, type that into your calculator. So 64 divided by 25 times 60, and we get 153.6 squared centimeters. Okay, and we'll move on to look at a volume scale factor. And again, this is really similar to what we did with the area scale factor, but it's a three-dimensional volume shape now, or capacity. So we've got two bottles of juice, similar in shape, and here the smaller one is 10 centimeters tall, the larger one is 19 centimeters tall. The smaller one holds a capacity of 300 milliliters. Find the capacity of the larger bottle. Okay, so capacity would be the volume of the bottle when it was completely full. That's what we're looking at here. Not the actual volume of juice, which you can see in the picture doesn't quite go right up to the top of the bottle. So volume and capacity, remember, slightly different things, but we're looking for the maximum possible volume or maximum possible capacity of this bottle here. Now again, when we start off, all we can compare is the height of the bottles. That's the only two common pieces of information we have. So we know the larger one is 19, the smaller one is 10. we're looking for the volume of the larger one, or the capacity of the larger one, and we're going to start off by comparing the lengths. So we're going to get a length scale factor, and it's an enlargement length scale factor, so 19/10. You could simplify that to 1.9 as a decimal if you wanted, or leave it as 19/10. It's going to be a calculator question anyway. To convert that length scale factor into a volume scale factor, we're going to take that number and cube it. Okay, so for the area scale factor, we squared the length scale factor. For the volume scale factor, we cube the length scale factor. Type that into your calculator, 1.9 cubed, and that's 6.859. Keep it accurate, don't leave out any numbers at this stage because it will make a big difference to your answer. So we're going to take that 6.859 and we're just going to say the volume of the bigger bottle is 6.859 times the smaller bottle, so times the 300 millilitres. Remember, a milliliter is a centimetre, a cubic centimetre, so here we could convert that quite easily. Times our scale factor and we get 2057.7 millilitres as our volume or capacity, the capacity of the bigger bottle if it was filled right up to the very top. Okay, and that's how you complete a volume scale factor question. Now, all the methods for length, area and volume are very similar. If it's an area or a volume, you've got this extra line because you've got to calculate the area scale factor or the volume scale factor in between before you multiply for the final line. So just watch out for that. Let's have a look at a little problem solving question. Quite commonly, these come up in these kind of similar triangles where one triangle is laid out inside another. What I would do, don't have to do this, but what I would do is draw the triangles separately. So you've got the smaller triangle, and it's just a sketch, it doesn't have to be a work of art. And then you've got the bigger triangle, roughly the same, but not really for me. Let's try that again, honestly. Something like that. Okay. Now if we look at the smaller triangle, this part here is 6 centimetres, this part here is x centimetres. The bigger one, that's the outside one we're looking at. Okay, the whole outside triangle is 8 centimetres here. Now this bottom line is x plus 6 centimetres. Now that's going to make things a little bit more complicated, but what we're going to do is start off the same way that we did before. What we want to do is find x. Okay, and there's a few different ways you can go about this, all based around the kind of comparison of similar shapes and their different lengths. We're going to try and stick as close as we can to the method we followed before. So we're going to start off by finding the length scale factor. Now the x on its own, just the x, is on the smaller shape here. Okay, so the x is on the smaller shape here. What we're going to do is we're going to use a reduction scale factor. So we're going to compare this kind of side here, the sloping side, with the 6 and the 8 because we know both of those sides, but we're going to do a reduction scale factor, which means the smaller number goes on top. So 6/8, which becomes 3/4 if we simplify that fraction. And what that's telling us is that the smaller triangle is 3/4 the size of the larger triangle. Now, what we want to find out is x. So that x value is going to be 3/4 the size of this side here. So 3/4 of x plus 6. Now that looks quite complicated, but actually it's just a simple linear equation. If we multiply both sides of the equation by 4, we get this. And that's just an equation to solve. So multiply out the brackets. 3 times x is 3x, 3 times 6 is 18. Take away 3x from both sides, and we get x equals 18 as our final answer. So x is 18 centimetres there. Okay, so that's one way to do that question. There are various other ways. What you can also do is you can compare the lengths of the sides and kind of work out, you'll end up with very similar working at the end of the question. So there are alternative methods for that. I'll show you one of them just here. So what we could say instead is, because we know these shapes are similar, then the kind of ratio of the sides to one another has got to be the same. So if I say 6/8, so this divided by that, that's got to be equal to this divided by that in the same order. Okay, now We want to try and remove the fractions here. The easiest way to do that is to cross multiply if you use that method, which means we're multiplying both sides by the opposite denominator. So here I'm going to get 6 bracket x plus 6 equals, take that one over there, 8x. Now essentially that's the same as this line here. Okay, it's just double the size. If we took it, divided everything by 2, we would get this line here. So we've got 6 multiplying it out equals 8x, and if we take away 6x from both sides, we get 36 equals 2x, and x equals 18 centimeters. So it's a very similar method, and that's how scale factor works. There's alternative ways you can go through this type of question. One might be more useful than the other in various situations. That's definitely the most tricky kind of question you're looking at there, though, with your similar shapes. For the other ones, you can just follow that kind of length scale factor, area scale factor, and then multiply process, and that'll work fine. Okay, hopefully you found that useful. For our maths videos and resources, please visit highschoolmaths.co.uk, and if you like the video, click that like button and subscribe, and please remember and share the video. Thanks for watching, and have a mathematical day.